So today we're doing area and Riemann sums. And we're going back in time. So normally you would start with this lesson, but I always teach you guys integrals first so you understand that you're finding area under a curve. And now what we're going to do is we're going to go back in time before they had integrals. Before integrals were discovered, mathematicians had to find out other ways to find the area under a curve between two values. Man, that's a typo. I'm going to fix that before I post it on you. Two values. Yes. We'll look at different ways that they have decided to try to determine the area. So for the first function, we have f of x equals x squared plus 3 from 0 to 6. So partition the interval 0 to 6 into 3 subintervals. So 0 to 6 into 3 subintervals and form the Riemann sum. Okay, so when we do the Riemann sum, what we have to do is we do this weird slanted E, and then on the bottom we go n equals from where we start at, which is 0 in this case, and to the top 6. And then what we're going to do is we are going to find the area from 0 to 6 of these little subintervals. So we're going to take f of xi, which is the length, because it's your y value, times change in x, which is going to be your width, which will make sense in a little bit here. It's not wanting to write it for me. Change in x, so that delta x. Okay, so that's what we're going to do. First thing we're going to do, though, before we try and figure this out, is we're going to sketch this. So I am first going to use red, and I'm going to do change in x. I have to find my change in x first. So what my x is going to change by. The formula for change in x is b minus a divided by n. Now what the heck is b, a, and n? Well, a is where you start at for your x, b is where you end. So you could look at it here as this being a, the 0, or the 6 being b, or a being 0, 6 being b. So it's the low x and the high x that we go to. Now n is how many subintervals we cut it into. So n equals 3. Okay, so we're going to cut this into 3 subintervals. So we have from 0 to 6, and then we're cutting into 3 pieces. So we're going to go 6 minus 0 divided by 3 equals 6 divided by 3 equals 2. So in order to cut it into 3 subintervals, we're going to actually look at a width of 2 on the rectangle, which will make sense in a little bit. So we have to sketch this graph. Okay, we're going to have to sketch from 0 to 6 the y values. So let's find them. F of 0 equals, we plug it into this formula, 0 squared plus 3. So f of 0 is at 0, 3. Okay, then f of 1 is going to be at 1 squared plus 3, which is actually 4. So we have a coordinate at 0, 3, and we have a coordinate at 1, 4. Then we have f of 2 equals 2 squared plus 3, which is 7. And so I get 2 and 7. Then I have f of 3. Oh my goodness, it's getting messy here. F of 3 equals 3 squared plus 3, which is 9. So I have a coordinate at 3, 9. F of 4 equals 4 squared plus 3, which is 16 plus 3, so 19. So I have a coordinate at 4 and 19. F of 5 equals 5 squared plus 3, which is 15 plus 3, which is 18. So 5 and 18. Nope, something's wrong. 25 plus 3 is 28. Oh my goodness, guys. So 5 squared is 25 plus 3 is 28. So 5 and 28. And then we get f of 6, which is 6 squared plus 3, which is 36 plus 3, which is 39. So my last coordinates at 6 and 39. So I'm going to plot those. Now I need to get to a y of 36, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines, so I'm going to make them each worth 4. So I'm going to go 4, 8, 12, 16, 20, 24, 28, 32, 36, and 40. Okay, so I'm going to plot these dots in, these coordinates in black. So I have 0 and 3, so it's approximately here. I have 1 and 4. I have 2 and 7. I have 3 and 9. I have 4 and 19, 3 and 9, 3 and 12. My goodness, I'm going to erase that. And erase this. 3 and 12, because 3 squared is 9 plus 3 is 12. 3 and 12. 4 and 19. 5 and 28. And then 6 and 39. So I'm going to try and connect these. Bear with me. All right. You can probably hear my daughter talking in the background. I'm sorry. It's as quiet as it gets during the day. All right. So that's the graph, and we are trying to find the area under that graph to the x-axis. Okay? So this one, the first method that they tried was left endpoints of each subinterval. So what they decided is, if I can break these up into rectangles, I could find the area of each rectangle and add them. Okay? We're cutting this up into 3 rectangles, because that's what 3 subintervals means. 3 rectangles, each with a width or a change in x of 2. So change in x along the bottom. So I'm going to have a rectangle. My first rectangle is going to be from 0 to 2. Okay, my next rectangle is going to be from 2 to 4. And my next rectangle is going to be from 4 to 6. And I'm going to end up with 3 rectangles, cutting this into 3 subintervals. Now this is where I need you to pay attention, because I'll lose a few of you. We have to use the left endpoint. So 0 to 2 is my one rectangle. I need to take the left side of it and make my rectangle. So the very left endpoint from 0 to 2 is this one, right? That's the very left endpoint. The one up here and the 2 would be the very right endpoint, and the one in the middle would be the midpoint. We don't want that. We want the very left endpoint. So I draw it over and I make myself a rectangle. That's going to be my height. So there's my rectangle, because I need it to be from 0 to 2 with the very left endpoint. So here's my rectangle. This is the area of it. Okay? Well, the area of that rectangle, width is the bottom. So each of these are going to have a width of 2, because change in x is just my width. But the length will change. What height is this pink at? Well, the height of this pink is at 0 and 3. Do you see this over here? The height is 3. This is 3, this little height up here. So the actual area of this rectangle with a left endpoint is going to be 3. 3 is my length, times 2, which is my width. So the area of that rectangle is 6. Now we're going to go to the next rectangle, because we split these into subintervals of 2, change in x of 2. So now I'm here. I'm between 2 and 4. Now I need to go to the very left endpoint. So this here is my very left endpoint. Here's my midpoint. Here's my right endpoint. So I want the left endpoint, which is here, in that interval between 2 and 4. So I'm going to follow it over to 4, and I'm going to follow it down. And this is my area with the left endpoint. This will make more sense, because we're going to do the right endpoint and midpoint for this one as well. Okay? So what is the width of this? The width is still 2, because it's from 4 to 2. This width is 2. The width of the last one is going to be 2. The width never changes. It's the height that does. Well, what's the height of this left endpoint? The height of this left endpoint is at 2 and something. 2 and 7. So my height is 7. So my length of this rectangle is 7 times 2. So the area of that rectangle is 14. Now we have one more rectangle left. It's from 4 to 6, so it's here. Okay, and we need to go to the left. So this is the 4 endpoint. This is 5's endpoint, which is the midpoint. And this is 6's endpoint, which is actually the right endpoint. I need the left endpoint, so it's this high. So I follow it over to 6, and I draw down. And I shade. So there's my area. And the area of that one, the length is at 4 and whatever its height is. 4 has a height of 19. So it's at 19 is my length times my width, which is 2. It never changes. So when I go to fill this in, this formula in, sorry I didn't need to do that. It's actually n equals a, b, x to the I change in x. So we can fill this in. So it's going to be, this means the sum of n equaling 0 to 6. And f of x, this is my f of xi. So I'm just going to put in xi plus 3, or x squared plus 3 if you want, and change in x in this case is 2. So we're going to sum up all the areas from 0 to 6, with xi plus 3 being my length if I plug in whatever xi is. Okay, so in this case, I was plugging in my left endpoints. I was plugging in 0, I was plugging in 2, and I was plugging in 4. 0, 2, and 4, and I got those left endpoints. So now I can just find the area of it. So I'm going to do my first box, which is 3 times 2, plus my second box, which is 7 times 2, plus my third box, which is 19 times 2. So when I add those all up, I'm going to end up with 58. So the area under the curve from the curve of x squared plus 3 from 0 to 6 with 3 subintervals, and the left endpoint subinterval is 58. What's the problem with taking the left subintervals? Well, this is the problem. Is it really calculating all the area under the curve? No, it's missing this area, it's missing this area, and it's missing this area. All the yellow is missing. So are we actually too little of area, or are we too much? Well, we're too little. So we know that the area under this curve is for sure more than 58. That's all the left endpoint subinterval is giving me. But people in the past were like, okay, well, this is a kind of way we could do it. Problem is, it's not really perfectly accurate. It just tells me that the area under this is more than 58. That's all that this really tells me. So then they said, well, what happens if we use the right endpoint instead? So we're going to sketch the exact same graph down here with the same coordinates. So we're going to sketch 0, 3. Oh, I have to label it first, sorry. 4, 8, 12, 16, 20, 24, 28, 32, 36, and 40. So I'm going to plot all those points. So I have 0 and 3. Maybe I'll zoom in a little bit just a second. 1 and 4. So all the same points we had before. 2 and 7. 3 and 12. 4 and 19. 5 and 28. 6 and 39. And we stop there. I know that the quadratic graph itself keeps going, but we're only looking from 0 to 6. Oh, that was bad. Erase that. This is really hard on an iPad, just so you know. Okay. Now this time, we're still doing subintervals of 2. So we still have 0 to 2 is one of our rectangles. And we have 2 to 4 is another rectangle. And we have 4 to 6 is another rectangle. Okay? But this time, instead of taking our left endpoints of each of these rectangles, which are these values, the very left-handed y of each of those, now we want to take the right endpoint, so the very right-handed side. So I go to the very right of this rectangle. So at 2 is the very furthest right I can go from 0 to 2. Oh no, those aren't supposed to show up. Dang it. Okay. So we're going to go to the very left, and it's going to go here. And we're going to follow it over and down. And we're going to take that area. Now that area is going to be 2 times whatever that y is. I got sidetracked. 7. 1 second. Go into my settings and fix that. So you get to see me in my settings. Hope you enjoy. So I want to take show previews never. No notifications here. We don't want any. None, 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 none. We don't want to allow any notifications from that. Nope, nope, nope. Sorry, Kaylin, you made it on here. I don't think you'll care though. Okay. So you have 2 times 7 is the one. Okay. And then we need to go to the green one. And the green one, we go to the very far right of it. And it is the y value that goes with 4. So we follow it up to the y value at 4 because that's the very right endpoint. And over the y value at 4 is 19. It's up here. Now we find the area of this rectangle, which is a height of 19, because at 4 my y is 19. So 19 times 2. So my width's 2 each time. I don't know why I went 2 times 7. I think it's because I got sidetracked from that notification popping up. So I usually go length times first. So length times width. 7 times 2, and then 19 times 2. And then blue, I'm going to follow it up the farthest right, up to its endpoint, which is 39. Follow it over. These are all the right endpoints. Okay. And so its rectangle height is 39 is the y for 6 times 2. The width doesn't change. So this one's 39 times 2. So if I want to do my summation notation, so my Riemann sum, I'm going to go from 0 to 6, my a to my b. F of xi, xi in this case is xi plus 3, and then my change in x was 2, because I found that out, b minus a divided by n formula. And then I just put my areas in here. So I'm technically doing x2, x4, and x6 as my y values because I'm taking the very far rights. So technically what I'm actually doing is I'm going f of 2 times the width of 2 plus f of 4 times the width of 2. And that gets me my area of my second rectangle. And then I'm going f of 6 times 2. That's indirectly what I'm doing. But if I draw the actual graph, it makes it easier for me to see. So f of 2 times 2 is actually 14, because it's going to be 7 times 2. F of 4 times 2 is 38, because it's 19 times 2, because f of 4 is 19. And then f of 6 times 2 is going to be 39 times 2, which is 78. Don't know why I just put in brackets. You're welcome. Okay, when I add all those up, I get 130. But what's the problem here now? Get out my little yellow. The area under the curve is all covered. That's good. We have all the area under the curve this time, but now I have all this extra. This is all taken into account, isn't it? So now I actually have too much area. So they figured out, okay, if I take a left Riemann sum or a right Riemann sum, sometimes I might have too little area, and sometimes I'm going to have way too much area. So now from those two, left Riemann sums and right Riemann sums, I know that the area of below this curve is at maximum 130, so it's going to be less than that, or at minimum 58, so it's going to be more than that. So I know the area should fall between those two. So that's what they discovered when they did left endpoints and right endpoints, that the sum of the actual area under the curve has to fall between those two. So then if they said, well, in this example, the left endpoints didn't give me enough. And in this example, the right endpoints gave me too much. They said, well, what if we take the midpoints of those intervals? So we're going to go to the next page. So we want to take the midpoint of each subinterval. So I'm still going to sketch it the same way I did. I'm going to plot my points. So I have 0 and 3. And I have 1 and 4. Oh, I have to mark my y's. I'll do that in a second. I have 2 and 7. Mark my y's. 4, 8, 12, 16, 20, 24, 28, 32, 36, 40. Okay, so I have 0 and 3, 1 and 4, 2 and 7, 3 and 12, 4 and 19, 5 and 28, and 6 and 39. Okay, so the graph has not changed this whole time. I have plotted the exact same graph, except maybe it looks a little different because my sketching sucks. But I've plotted the same thing, okay? And I went pink, green, blue. So I'm going to follow the same thing again. Pink, green, blue. So pink was my first width of 2. Green was my second width of 2. And blue was my third width of 2. Could they have done it in less than 3 subintervals or done it in more than 3? Sure. But I picked 3 because they were the nicest to deal with. So if I pick 0, that's the far left-hand endpoint. If I pick the y for 2, that's a far right endpoint. But if I take 1 in the middle, that's my midpoint. So I follow 1 up to my y, right here. And now I make my rectangle with that as its height. So I follow it over. So there. Now look, I'm missing a little below. I'm missing a little below here, right? But I have a little extra above. So are they going to balance each other out? I don't know. We'll see. So what is the area of this rectangle? Well, the width is still 2. The width doesn't change the entire time. Our change in x is always our width. Our height in this case is at 1. And f of 1 has a height of 4. So the height of this one is at 4. That's my length times my width, which is 2. Now I'm going to go to my green. Okay. My green is here because I'm going to take my midpoint height. So I'm going to follow it up, and that's going to be my height, and it's going to follow over and finish off my rectangle. Now I'm going to shade it. And that is going to be a height of, at 3. F of 3 has a height of, can't remember, 28, 12. F of 3 has a height of 12. So the height is 12 and times the width, which is 2, it didn't change. Then my blue one, I'm going to go to my midpoint, which is 5, because it's between 4 and 6, follow it up, and that's going to be my height. Follow that over both ways, and I have my new rectangle, and that's my area, which is going to be the height at f of 5, which is 28. So I'm going to get 28 times 2. Okay. So when I go to do my sum formula, it's going to be from n equals 0 to 6. F of xi, well, xi, when I fill it into the original formula, is x plus 3, or x squared plus 3. Was it x squared plus 3? It should be xi squared. This whole time I've been messing that up. Xi squared plus 3. Let's go back to that previous two, because you're supposed to be filling into the x squared plus 3 formula. So this should be xi squared plus 3. So should this one be xi squared plus 3. Sorry, it's supposed to go into the original. I missed the squared. But my change in x for all 3 of these has been 2. Okay? So what are we actually doing? If we want to show the work, we're going f of our midpoints. So we used 1, we used 3, and we used 5. So we're going to do length is f of 1 times 2. That's our first area. Plus f of 3 times 2. Plus f of 5 times 2. F of 1 is 4 times 2. Plus f of 3 is 12 times 2. And a dead spot on my iPad. Plus f of 5 is 28 times 2. Which equals 88. Now you might say, oh, okay, that's it. That's the area under the curve. Well, let's see. So when we take the midpoint, for the first one we had a little bit above, a little bit below. For the green one, we had a little bit above and a little bit below. For the blue one, we had a little bit above and a little bit below where we didn't catch. So they kind of look like they maybe balance each other out. Well, how can we check what the real area is? We've already found out how to find the actual real area. This was before them knowing how to find the real area. So we can check and see what is the actual area. We use the integral. It's from 0 to 6, right? And it's x squared plus 3 dx. Right? Okay, so let's try it out. So we're going to go math, and we're going to pick number 9. And I'm going to go from 0, so if you have the fancier calculators, the new ones, 6 x squared plus 3 dx. Usually you have to put the x in that spot. This calculator, you don't have to. And I get 90. And 90 is my actual answer. So the answer to this is actually 90. So, and we got 88. We got very, very close with the midpoint. So what they found out is the left hand and right hand endpoints will get you what get you a kind of a minimum maximum area possible. The midpoint gets you extremely close, and the midpoint will get you completely close and exactly accurate if you actually split this into more subintervals. If you actually split this into an infinite number of little tiny rectangles where you took their midpoints, then it would get rid of more of this above and below extra missing, and you'd get 90. So what they found is if they increased the subintervals, so in this case we only picked 3 subintervals and did 3 rectangles in here, so we had more extra above and more missing below. What they figured out is if they actually made it an infinite number of them, then they would get extremely close to the actual answer, and you would get 90. Well, the quickest way they figured out how to do that is that was where the birth of integrals came in, where they realized, hey, if I take the integral of it, I'm actually taking an infinite number of these rectangles, and I can find the area under the curve without having to do an infinite number of rectangles. Can you imagine how much time that would take? How much time this took to just do 3? Can you imagine if we did 100? We'd be using really tiny numbers too. Okay? So that's an example. Example 2 is the exact same thing, except it's from 1 to 9. It's x minus 3 squared dx, and I'm partitioning between 0 and 9 with 4 subintervals of equal length of 2. Well, we can find that out. So if you got the first part and you're like, dude, I have this, I just want to copy notes, I'm putting the actual filled in version of notes online so you can go look. Or if you're like, I got this, I don't need the other example, good. You can go right to doing the work. If you're like, man, I just need to see another one, here it is. This is the second example, okay? So if they're asking me to approximate 1 to 9, x minus 3 squared dx by partitioning 1 to 9 into 4 subintervals, I can't just go to my calculator and give an answer. So on the AP exam, they would ask for a left Riemann sum or a right Riemann sum. And if you just got the correct answer from 1 to 9 x minus 3 squared by doing the integral or using your calculator, you will be wrong. Because using the left Riemann sum won't actually get you the real area, right? So they will ask on the AP exams and on university exams, they'll ask for the left Riemann sum or the right Riemann sum, and you need to be able to find those. So if all you know how to do is integrals, you're going to be in trouble. Okay, so we're going to go through this. So we have to first find our change in x. Our change in x is always b minus a divided by n. This is a, this is b, this is n. So it's going to be 9 minus 1 divided by 4, which is 8 divided by 4, which is 2. So again, I have a change in x of 2. Does that mean I'll always have a width of 2? No. Sometimes it's a change in x of 3. Sometimes it's a change of x of 1.5. You hope for a change in x of an even number so that when you have to do the midpoints, they're not decimals. Okay? So you always want to change in x of an even if you have a chance. Okay? This one did say equal length of 2. I was just being nice, but you're going to have to be able to find it yourself with the change in x. So what did we do with the last one? We found from 1 to 9 all of our y values so we can sketch it. So that's what we're going to do first. Oops, I haven't done that in a while. Okay, so we're going to do f of 1. We're not starting at 0. This time we're doing f of 1. So we're going to get 1 minus 3 squared, which is negative 2 squared, which is 4. Then we're going to do f of 2, which is 2 minus 3 squared, which is negative 1 squared, which is 1. F of 3 equals 3 minus 3 squared, which is 0 squared, which is 0. F of 4 equals 4 minus 3 squared, which is 1 squared, which is 1. F of 5 is 5 minus 3 squared, which is 2 squared, which is 4. Oh my goodness, that's bad. 4. F of 6 equals 6 minus 3 squared, which is 3 squared, which is 9. F of 7 equals 7 minus 3 squared, which is 4 squared, which is 16. F of 8 equals 8 minus 3 squared, which is 5 squared. Which is 25. And then f of 9 equals 9 minus 3 squared, which is 6 squared, which is 36. Okay, I'm going to plot all these. There's more numbers this time. Okay, because we're 4 subintervals instead of 3. So I'm going to go 4. Oh, it's reset me. So I'm going to go 4, because I figured out already that this will be enough. 8, 12, 16, 20, 24, 28. Nope, that's messy. 28, 32, 36, 40. Okay, then I'm going to plot my points. So I have 1 and 4 as my first point, 2 and 1, 3 and 0, 4 and 1, 5 and 4, 6 and 9, 7 and 16, 8 and 25, and 9 and 36. And now I know I'm right because this is x minus 3 squared. My x squared graph starts at 0, 0. This one's been moved 3 to the right. So my vertex is normally at 0, 0. It's now at 3, 0. So I know I'm correct. And I sketch it. Now I'm trying to, find the area under the curve of that. But in this case, using left Riemann sums. And my width is 2. So I'm going to go from 1 to 3 as my one width, because that's a width of 2. And then I'm going to do 3 to 5, because that's a width of 2. And then I'm going to do 5 to 7, because that's a width of 2. And then I'm hoping my last width of 2 finishes it off. So 7 to 9 is a width of 2. 1, 2, 3, 4 subintervals. So I know I'm not wrong. Okay. Now we have to use the very far left endpoints, because we find the left Riemann sums. So this is my left endpoint for the first one, because 1 is the very far left I can go. So I follow that over and make myself a rectangle out of it. Now the height of that one is at 4. My y is 4. And my x is 2. So I'm just going to put an arrow because it won't fit in here. So it's going to be 4 times 2. So the area of that rectangle is 8. Then I need my left Riemann sum for my blue. The problem is that my left Riemann sum is 3. And my y at 3 is 0. So I literally just have a straight line. And a straight line has an area of 0, right? Because its height is 0 times its width, which is 2. So the second box has an area of 0, because I'm using its left Riemann sum. Then the green one's left Riemann sum is whatever the y is for 5. So I follow it up and over. So the area for the green one is going to be a height of 4. So length of 4 times 2. And then the red one, I follow the very left up. The very left is the number 7. So I follow it up to its y and over. So it's going to be at 16 times 2. Now, this case, left Riemann sums are actually all, most of them are missing. Like they're actually shaded lower. But this pink one is actually shaded higher. So left Riemann sums aren't always less area. Sometimes they're more. It depends. If the graph was concave down, the left Riemann sums would be actually a larger area than the real area, and the rights would be a smaller area than the real area. So because this is concave up, we're going to end up coming out too small of an area. Okay, let's write our summation notation. Our summation notation is from n equals 1, from our a to our b, which is 9. And then f of xi, well, the x just gets replaced with an xi, so you're going to get f of xi minus 3 squared times the change in x times the number 2. Okay? And so what we're going to get is our left bound x's if we want to show all the work. So our left bound x's are the number 1, the number 3, the number 5, and the number 7. So we're going to do f of 1 times 2 plus f of 3 times 2 plus f of 5 times 2 plus f of 7 times 2. F of 7, that's really messy, sorry. F of 1 is 4 times 2 plus f of 3 is 0 times 2 plus f of 5 is 4 times 2 plus f of 7 is 16 times 2. So we're going to actually end up with 8 plus 2 plus 8 plus 32, which is 48. And we know we're too small because if I shade the rest of the area underneath, I'm missing this part, this part, this part, and I was only a little above over here. So the above does not outweigh the below that we're missing, so this area is too small. Now we're going to do the same thing, but we're going to do right bound. So we're still going to have to plot all the points. So we're at 1, oh, I'm going to get the black marker. So we're at 1 and 4, 4, 8, 12, 16, 20, 24, 28, 32, 36, 40. So we're at 1 and 4, 2 and 1, 3 and 0, 4 and 1, 5 and 4, 6 and 9, 7 and 16, 8 and 25, 9 and 36. Oops. Put my hand down. Okay. Now we need still the same width. I don't know if I'm using the same colors, but that's what I'm going to do. So I need a width of 2. But now I'm going to use the right extreme endpoints and their y values. So my right extreme endpoint is 3. Its y value is 0. So this is going to be a straight line here. So the area of this is going to be 0 times 2. The blue one, I go to its far one, which is 5, and I follow it to its y and over. So it has a y of 4. So now I'm overcompensating. I have too much area. So that's going to be 4 times 2. The green, I'm going to go to its far right, which is the 7. 7 is at 16. Follow it over. Once again, I have too much area again, so I'm overcompensating area. This is going to be 16 times 2. And then my red, oops. My red's overcompensating again. So too much area. And its y is at 36 times 2. So I'll write out the equation. The equation is going to be I've been writing n the whole time. It's i's. That's going to suck. Let's go back. These should be i's, not n's. I equals 0. Because it's xi. I equals 0. So sorry. It's because of the n and the change in x formula. I just used an n for some unknown reason. It's I because you're filling it in for the I, right? Oh my goodness. I, not n on the bottom of the summation. Error. So it's x equals I. I think I caught it now. I don't know why I was writing here. X equals I from 1 to 9. Because we're doing f of xi, not f of xn. If it was f of xn, then I could put n equals 1. I don't know why I did that. Idiot. Okay. So it's going to be f of xi. Hence why this needs to be I equals 1. Dummy. Change in x. So in this case, it's going to be 9. I equals 1. So from 1 to 9, f of xi is going to be xi minus 3 squared times 2. And in this case, we're using 3, 5, 7, and 9. So I'm going to do f of 3 times 2 plus f of 5 times 2 plus f of 7 times 2 plus f of 9 times 2. F of 3 is 0, so I get 0 times 2. F of 5 is 28. No. Yep. No, that's a different one. F of 5, what the heck is F of 5? F of 5 is at 4. And 2. F of 7, if I follow it up, is at 16. And 2. And f of 9 is 36 times 2. And when you put that all in, you get 112, which is too much. You can blatantly see it's too much. This is not under the curve. This is area not under curve. This is area not under curve. And yes, I know we're missing this little piece, but it doesn't balance all the other areas we're missing. Okay, one last one, midpoint. So we plot all those same points again. So we're going to get 4, 8, 12, 16, 20, 24, 28, 30, 4, 8, 12, 16, 20, 24, 28, 32. Wow. 36, 40. Okay. So we're at 1 and 4, 2 and 1, 3 and 0, 4 and 1, 5 and 4, 6 and 9. Too many papers in front of my face. 7 and 16. 8 and 25. 9 and 36. Okay. Do our 2 intervals again. So our width of 2, because that was our change in x. So we're going from 1 to 3. 3 to 5. 5 to 7. 7 to 9. But this time we're taking the midpoints. So I'm going up to the height of 2, wherever 2 is at. 2 has a height of 1. So I'm going to just do this. So the area of that one is going to be 1 times 2. Then I go to 4. 4 has a height of 1. Again, so this one's 1 times 2. Green, I'm going to go to 6 because it's in the middle. It has a height of 9. Oh my gosh. If my hand touches the screen, it tries to send it to a new page. So this is 9 times 2. And then the red, oops, I go to the middle, which is 8. Follow it up to 25. And over and down. And so I have some extra above and some extra below. And this one's going to be 36 times 2. So we do our sum formula. I equals 1 to 9 f of xi minus 3 squared times 2. And our values we're going to use this time are 2, 4, 6, and 8, the middle points. So I'm going to get f of 2 times 2 plus f of 4 times 2 plus f of 6 times 2 plus f of 8 times 2. Because f of 8, f of 6, f of 4, and f of 2 are the lengths. F of 2 is a height of 1, so I'm going to get 1 times 2. F of 4 has a height of 1, so I'm going to get 1 times 2. F of 6 has a height of 9, so I get 9 times 2. F of 8 has a height of 36 times 2. F of 8, 36. No, it doesn't. 25. This height is 25, Crystal. Ah, I hit the arrow again. Goodness gracious. It's 25 times 2. So I'm going to get 2 plus 18 plus 50, which gets me 72. Now, if they ask you on the AP exam or on your university exam for midpoint, and you or right left sum or right summation or left summation or midpoint, and you give them the actual integral, you didn't do what they asked and you will get no marks, okay? The midpoint is very close, but we'll see. So we can check this out. We can go from 1 to 9, and we put in x minus 3 squared dx. I'm going to go math down to number 9. I'm going to go from 1 to 9, x minus 3 squared. And then you're going to have to put an x in the dx's spot. You hit enter. I didn't want to put it in y equals. What the heck? 9. Oh, it's because I'm this stupid new calculator. Math 9. 1 to 9 bracket x minus 3 bracket squared. And then you're going to have to put a dx in there. Enter. And it's 74.666666 repeating, right? That's the actual area under the curve. Or in a fraction, it is 224 over 3. So that's the actual area under the curve, right? If they took an infinite number of midpoints and they found it that way. So 72 is very close, but if you give them an answer 74.6 on your final or on your unit test in university or on your AP exam, they would give you no marks because you didn't actually find the midpoint. You found the integral and they know you did. So that's how they can test and see if you use the right Riemann sum or left Riemann sum or midpoint, because your answer will not be the integral. It might be close, but it won't be the integral. So if you give them the answer to the integral, you're giving them the real answer to area under the curve. Now you might say, well, why are they making us do this? And because it's important to know where calculus came from, not just where it's at. And this gives you a better understanding of what the heck you're actually finding when you're finding the integral and I tell you you're finding the area under a curve. Okay? So that's the end of this lesson. The next lesson is slope fields. And because I'm sending you off into the real world, I want you guys to have a glimpse into Khan Academy and what it has available for you for university. Because sometimes you don't understand what was taught to you in class and you need to go home and look at a resource that can maybe help you. So for slope fields and for volumes of revolution, I'm going to use Khan Academy links for you guys to watch just for 2 lessons out of the entire year, just because I want you guys to have a glimpse into what you could possibly use next year, whether you're in chemistry or you're in physics or bio or maths in university. You can Google the topics that they're teaching, and they have little lessons and they have little questions at the end if you want to take those as well. But I'm going to assign homework questions from your textbook for you to work on, and I'm going to give you an assignment myself for you to hand in like normal. But just 2 of the lessons for this year, I'm going to have you look through the Khan Academy videos just to get you guys familiarized with that, so that next year you do have a backup plan if you come home from class and you're just lost, okay? Or if you come home from class and you need a little more clarification. So your lesson on Thursday is going to be some Khan Academy links. And then next week is a review assignment. The week after that, we're going to do area between 2 curves, not just area under a curve to the x-axis, area between 2 curves. So I could give you 2 quadratics and ask for the area between them and how much area there would be. And then our last lesson is volumes of revolution. Okay? And that's going to be like a little 2-week lesson because volumes of revolution is quite a bit of little lessons to watch, and it's very important and it's kind of intense, and there's no way that I can sketch in 3D like Khan Academy can. So when I decided to do 2 videos for you guys to see how you could possibly use the internet to your advantage, Khan Academy is great for university. I decided to do volumes of revolution because I just cannot draw 3D like that guy can. He's like an artist really in 3D drawings. So Thursday's lesson is going to be links that I'm going to get you to watch, okay? Next week, after that is a review assignment with no new lessons. You're welcome. The week after that is going to be area between two curves. Then the next 2 weeks after that are volumes of revolution. And then you end up with just a review assignment at the very end of the year. And we're done. We're going to be done. It's going to be so fast. And I really do miss you guys. And I wish I could see you guys every day because I miss the laughter and I miss the funny. And I don't really have that right now. I do still get it from you guys sometimes through emails and through Google Classroom. But I do miss every day having some really good laughs. I hope you guys have a really great week, and I miss you.